All right, so here's a piece of notation. I'm going to write AI to denote the fraction of the total amount of item I that the thief takes or that I take. And so, you know, if we want to think about, like, suppose we have A2 equals a half, then what this means is that the thief walks into the warehouse and sees this item 2 and says, I'm going to take half of that. Okay, so let's think about then how much weight this costs in his backpack. Well, if he just took half of item A2 and the total weight of item A2 is 3, taking half of it means he's going to put 1.5 pounds in his backpack, which is just 3 times the fraction that he took. Okay, so the weight of item I that he takes is the total weight that's there times the fraction of the total weight he takes. So if AI is 1 for any of these items, then he just takes the whole weight, right? All of the stuff that's there. And then the same logic goes to the value. So if we think again about item 2, we know that if he takes all of it, the value is 12, right? The total value of item 2 is 12. So if he takes half of item 2, then the value he gets is 6, which is just the value of that item times the amount that he took. Okay, so you could also think about A as like amount instead of a fraction. But in any case, the problem statement here, the optimization problem statement of the fractional knapsack is almost identical to the optimization problem statement of the 0-1 knapsack, right? The goal here is to select these A's, so A1 through AN, to maximize. So I'm going to say maximize A. So I'm going to call A this whole thing. So A is the tuple of all the A's. So I want to maximize over all feasible A's. I want to maximize the sum over all I's of the AI VI. And so now notice that I'm adding over all I's. I'm not adding over the subset selected, because the subset is now baked into my A. So if I don't take any of a particular item, then that A is 0, right? That coefficient is 0, right? So if I take only all of item 3 and all of item 4, then the way I express that is I say A1 is 0, A2 is 0, A3 is 1, and A4 is 1. Okay. So this is just a generalization that's cleaner in some ways than the 0-1 knapsack. So my objective is to maximize this subject to the constraint, right? Subject to, for all I, AI is between 0 and 1. And also the sum over all I of WI, AI is less than or equal to the total capacity of the bag. Okay, so there's my optimization problem right there. I'm maximizing over these length n tuples subject to the following constraints. And these following constraints, there's one more actually. I want to just make sure that it's in here. Oh no, there isn't. This is not a probability distribution, right? So I get to take any fraction of any of them, and my capacity constraint controls these A's from being too large. All right, or from too many of them from being zeros. And so if you want, we could also actually rephrase the 0-1 knapsack in exactly this language, right? So the 0-1 knapsack, what does that do? Well, all it does is it changes this one constraint. So this is just an aside, but I want to make sure this is clear. You can very often think about, I'm going to change this to blue. You can very often think about the differences between these kinds of problems as just being differences in the constraints, right? So if I were to try to phrase the 0-1 knapsack in terms of this same language, what I would do is I would say, rather than the interval between 0 and 1, rather than that being like the rule that I place on my AIs, I would say only select 0 or 1, right? So select AIs from the set 0 and 1. And so this is just a pure aside, just for your benefit. The 0-1 knapsack is the same with this change, has this, right? What's the difference? Square brackets versus braces, right? The braces is a discrete set that contains exactly 0 and 1. Those are the only numbers in the set. The square brackets, however, describe a closed interval. So every possible number between 0 and 1. Anyway, there's our optimization problem. Now let's think about what a greedy algorithm might do. So here's the greedy idea. Greedy idea says, let's take the most dense item we can, right? The thing that has the highest per unit value, and take as much of it as we possibly can. So we want to maximize the efficiency of our use of space. So maximize the per unit value of taken items or taken stuff. Okay, so that means what we're going to do is we're going to look at our per unit value column here, the right column, and we're going to sort by this, right? So we're going to sort decreasing by this, and then just go down the list, right? So what we'll do is we'll take the most we possibly can fit of this stuff, and then the most we can possibly fit of this stuff, then the most we can possibly fit of this stuff, and then the most we can possibly fit of this stuff. And then if we run out of stuff to take, then we are done. And if along the way we run out of space to fit more stuff, then we stop. Right? We just max the capacity with whatever we have left and walk away. That's the greedy algorithm. Right? That's the greedy idea here. Okay, so let's think about how this would actually go, and let's actually do some math here. So our step one is basically going to be let's look at the thing that has the highest per unit value, which is 3, and let's just take as much of it as we can. So how much can we take? Oh, we could take it all, right? We have a capacity of 10, and the total weight of this stuff is 4, so let's take it all. So if Wi of the stuff of highest per unit item fits in remaining capacity, take it all. Okay. Otherwise, take as much as fits. Right. Take whatever you can fit. Then repeat. Here, I should move this over. So then repeat. Else, take as much as possible. I'm just going to, no, this isn't step 1, this is just the step. As possible. And return. Okay. All right, so here we go. Let's walk through this thing. So our step 1 says, we've already thought about this, right? There's 4 units of the most valuable stuff. Our capacity is 10, so we take it all. So we let A, let's see, we let A3 equal 1, right? So we max out item 3. Okay, so item 3 is 1, and now we want to say what's our remaining capacity? Capacity is W minus W3A3. Well, this equals 10 minus 4 times 1, so that's 6. So now we have 6 units of space left. So now let's look at the other items that there are. So what's the next most valuable thing? Well, the next most valuable thing is, oops, I didn't mean to erase the entire box there. The next most valuable thing is this one. Okay, so we have 6 units of capacity left. There are 7 units of this stuff. And so what does that mean? It means we can't take it all, but we should take as much as we can fit. Right, so how much can we fit? Well, we can fit 6/7 of what's there. Okay. If you want, we could fit 6 pounds of what's there. Okay, so here in our step 2, take as much of item 1 as we can fit. One as fits. That is, i.e., A1 should equal 6/7. Okay, and so what does that mean? Well, let's just verify that now our remaining capacity is 0. So our total capacity was W minus W3A3, now minus W1A1. And so this piece here, we already know is 6. We computed that above. So this is 6 minus W1 is 7. Right? The total amount of item 1 is 7 times 6/7, which is the fraction of item 1 that we're taking. And this clearly equals 6 minus 6, which is 0. Okay. So we've just maximized the amount of stuff we could take. And now let's think about how much value we got. So what did we do? We took all of item 3. So let's think about our total value. And we might as well go from our objective function here. So we're going to sum over I. So I equals 1 to 4 of VI AI. What is our solution? Well, our A's equals 6/7. 0, we didn't take any of item 2. 1, we took all of item 3. And 0, we didn't take any of item 4. And so our total value that we took is going to be equal to 6/7 times, I think, 42 is the total value available of item 1. So 6/7 times 42 plus 0 times 12. That was the total available value of item 2. Plus 1 times 40 plus 0 times 25. Okay, and you can verify for yourself if you have a piece of paper and some notes. You can verify for yourself that those numbers match up our original problem. Okay, so what is 6/7 of 42? Well, 42 divided by 7. Do a little bit of math in your head there, and you'll find it's 6, right? So 1/7 of 42 is 6. So 6 times that is 36. So we took a total of $36 worth of item 1, plus all of the other one, all of item 3. And so we took a total value of 76. Okay. So that's the value of the objective as achieved by the greedy algorithm in this case. So the question is, there's two questions. First, I think it's interesting to ask, how does this compare with the best we could do in the 0-1 case? Well, in the 0-1 case, so I'm going to do this in blue again, the 0-1 solution was to take all of, you can only take all or nothing. So the 0-1 solution was to take item 3 and item 4. And so let's just actually use our same objective formulation here to see what that is. So the 0-1 solution says take A, and I'm going to call this 0-1, take A equals 0, 0, 1, 1. So all of item 3, all of item 4, and none of item 0, none of item 1, none of item 2. And so for the 0-1 solution, and this is the optimal solution, keep in mind, the solution is I equals 1 to 4 of VI of AI 0-1. And so that's 0 times 42. So that's a qualitative massive difference between this solution and the other one, that we didn't take any of item 1 in the 0-1 knapsack, but we took almost all of it in the fractional knapsack. So nothing of 42, nothing of 12, and then all of 40, and all of 25. And what does that add up to? 65. Okay. So let's just ask ourselves for a second, why did we do better in the fractional knapsack than in the 0-1 knapsack? Right? So here's our observation. Right, for the same problem, all the same numbers, the fractional knapsack outperformed the 0-1 knapsack. Fractional outperforms 0, 1. Okay, why? Well, let's think about what the constraints are in the problem. Right? This is actually a very useful exercise. If you haven't thought too much about optimization before, this is something you should always keep in mind. Recall the difference between the constraints in our two problems. Right? The only difference between the fractional knapsack and the 0, 1 knapsack is this constraint. Okay? In the fractional, we're allowed to take any number between 0 and 1 for all of our a's. And in the 0, 1, we're only allowed to take zeros or ones. Okay, so which of these two problems has a larger set of feasible solutions? And by that I mean, which of these two problems has a larger set of solutions that don't violate the rules? Well, this one, right? This one has looser constraints, right? Less restrictive constraints, so there are more feasible solutions. So here we have looser constraints than 0, 1 version, right? The constraints are looser, which means that there are more solutions allowed. And what it means that there are more solutions allowed is that the quality of those solutions may be better. Okay? There are more solutions, and so it is possible that the quality of those solutions is better. And in particular, it's actually impossible that the quality of the solutions is worse in the fractional knapsack. Okay? And so this is a fundamental fact of optimization. If you loosen your constraints, you improve, at least weakly, you improve the quality of your solutions, right? That is a fundamental fact of optimization. The space of feasible solutions is larger for the fractional knapsack because you're allowed to pick fractions. And that's why 76 is bigger than 65. So there's been a lot of kind of like extra optimization theory stuff in this lecture. And so if this interests you, I encourage you to reach out and we can talk about how to expand your knowledge of this stuff further. We'll think a little bit more about it as we go on in the course, but it's an important topic that you should certainly explore if you find this interesting. Back to greedy algorithms. Now we need to ask ourselves, did the greedy algorithm do best? Right? We know that it did better than it would have if it had been constrained to just taking whole items. But, is this optimal? Is there anything else that could have been better for the fractional knapsack problem than what the greedy algorithm gave us?